So, what we are going to do today is a bunch of problems, of examples of one-dimensional systems, and we'll start from the easiest, simplest case, which is a free particle. What do I mean by a free particle? Very simple. Does Vx necessarily have to be zero in order to be a free particle? No, could be also 7, any constant, it doesn't matter, it just shifts the energy. The only point is that it's not a function that has some structure. Constant is fine, the same conclusions. So, in principle, what do I mean by, usually by solving the problem of a free electron or any other problem? If nothing else is specified about the problem, I want to find the eigenvectors and eigenvalues of the Hamiltonian. Or, in other words, find the solution of the stationary Schrodinger's equation. Okay, so I can write down the differential equation and I can solve it. Really no problem. But I want to save some work and note that basically for a free electron, H is equal and since the commutation between px and px squared is equal 0, can conclude actually two things. One thing is that momentum is conserved in this problem. And second, I know already the eigenfunctions of the momentum operator, therefore I know also the eigenfunctions of the Hamiltonian. So, as we have seen previous, this is the whole basis of the momentum operator, as we have seen in the previous lecture. So therefore, this is also the eigenfunctions of the free particle Hamiltonian. What does change, and as we have said in the previous lecture, while the eigenvectors, the eigenvalues for the momentum was kx, what is the eigenvalues for the free electron? Well, exactly. How do I know it? simply remember that this is the definition of the Newtonian. And therefore, just substituting psi k here will give you the values of E. Therefore, k squared and the constants. So we know everything that should be known about a free electron. Let me just plot the eigenvalues. So as function of k, and k here is continuous, I'll get a parabola. No quantization of the energy, because any value of k is possible. Therefore, any energy above 0, if we change that with a constant, above a constant, is permissible. What will happen if we'll do periodic boundary conditions? Will something change?
Yes, it's going to be quantized.
Exactly, it will be quantized. If you remember, the previous lecture we saw that kx in this case would be nothing else will change, but the result of this behavior is comes at distinct and so on and so forth. And we have a discrete bunch of eigenvalues of the energy. Okay. That's always right in quantum mechanics. If your space is infinite, you have a continuum of the energy. If you have some kind of finite space, you'll have quantization. Of course, at the limit that Lx is taken to infinity, they'll merge. What else can I say about this spectrum of the energy? It's degenerate. If I give you a value of energy, you have two possible k's that describe it, plus and minus k, because it's just squared of k. Why is it? Simple physical reasons. There's no difference between an electron or any other particle moving to the right or moving to the left, going clockwise or anti-clockwise on the periodic boundary condition. Okay, now let's say I prepared a wave packet of this particle. particle or electron in one dimension. So at time t0, I have some wave functions that describes the system. How will it evolve with time? There are two ways to approach it. The difficult one have some initial conditions. I have a differential equation. Go on, solve it. A bit more sophisticated is to use the fact that basically I know the eigenfunctions of the Hamiltonian. And as we have shown, sum over all the eigenstates of the momentum, okay, have the amplitudes at time t equals 0, use the phase, the development in time, and write down the eigenfunctions. Okay, what am I missing here? One thing that is trivial I know the energy. And the second is this amplitude. How do I find the amplitude? Fourier transform at time t equals 0 when I have my initial conditions. So okay. Now, if you are considering doing it on a computer, this is much more efficient. Someone can explain me why? Please.
Wait, okay, sorry, actually I shouldn't.
Okay, how do I solve a differential equation on a computer?
I actually don't have an answer. There you have two variables, and when you use numerical methods, you usually take a continuous variable and divide it into discrete intervals, right? Numerically. There, in the original equation, you have two variables. So you have to divide time and space into discrete numerical units. But if you want to calculate an integral, then let's say using Simpson's method, then the division is going to be one dimensional over the variable over which you integrate. So it's much less points.
Correct. And moreover, here, if you want to see how it develops at some faraway time, you have to go step by step through T. You accumulate mistakes. Here, you just stick any t's that you want once you perform the Fourier transform, and you can get the behavior at any time that you want in one shot. So it's much, much more efficient. So whenever you can find the basis of a problem in order to describe the behavior with time, use it. When doesn't it work? I didn't speak about it now, but I spoke about it.
Can you repeat the question?
Excuse me?
Can you repeat the question?
When doesn't it work?
The formula or numerical?
This whole procedure, even the formula.
When the momentum operator commutes with energy?
No, I'm talking about general, not even necessarily this Hamiltonian.
When you don't have
Maybe there is. We need to talk about E of n.
You're picking around it.
You mean that when the spectrum is discrete?
No. The spectrum discrete is fine. So and so on a computer you can do it only for.
And the potential is not only in space, it's also in time.
Exactly. Then this whole behavior, as we said, that comes out from solving the stationary Schrödinger equation. If not, there are methods that start with a phase and put it down as small corrections, but then it's not as efficient. You have to go step by step and see the development of that. In general, problems that have time dependent are much, much more complicated than problems that have stationary potentials. Okay, let's do an example. Okay, so what I want is basically taking a specific wave packet at time t equals 0. Okay, so it's a Gaussian. can guess already why I chose a Gaussian.
Sorry?
Why I chose a Gaussian?
Because
Stays
the
the
Fourier
Gaussian.
transform of the Gaussian is a Gaussian.
Exactly. And there's also a physical reason, because that's a usually quite good description of a wave packet that is more or less localized at some point. Around which point is this localized?
X equals
Still
0.
zero.
X equals 0, of course.
And also it minimizes the uncertainty, right?
I'll show it in a couple of steps. Yes. Okay, where did I get this value? Just from normalization. So, A of k, and I'm showing that basic. Someone will lose his head here. If you want to open it a bit,
It's fine.
So, the second reason I'm doing it because it has a mathematical trick how to perform these integrals that you run into it continuously in a lot of other problems in physics. So I'll do it in detail. And here I'll put the squared. So I just wrote it down. So someone knows how to perform this integral,
Completing the square.
completing to square. Okay, what happens here? X square over 4 delta 0 square. I get it immediately. This guy squared is omitted by this guy, and I forgot for a minus also. That's okay. And the guy in the middle, you square it, you get 4i kx delta 0 square, which is exactly this term.
It's supposed to be not really important. dk
Integrand
divided
or
by the square root
divided
of
by-
the just the
dx. Oh,
dx, yes. Mistake.
Okay, so what's nice about this? This guy doesn't depend on x. Move it before the integral. should have told me. Okay. Please follow my math as you see,
Decay is good.
and your favorite dx.
Dx. Why is it also?
Okay.
I have something with decay.
Okay, this is a constant. So as long as I'm from minus infinity to infinity, I can just replace this guy by u, this guy by du, and that's just our usual Gaussian integral, which if you need to learn any integral by heart, this should be it. So you have here a Gaussian. Just remember that if you really want, you can replace it with the constants and get exactly the questions?
We say the integral is just going to 1. Ah no, it's... Wait.
Did I forget a constant here?
Why the integral goes to...
What is this integral?
It's
Is delta function?
the square
No,
root
no,
of
no,
pi.
no, no,
So,
no.
we assume it's okay.
Okay, that's what I said. If you know any integral, this minus infinite to infinite of dx e to the minus ax squared.
This is the square root of pi.
Pi over A.
Yeah, pi over.
Square root pi over a, and if I didn't botch the constant here,
No.
and if you want to know how to do it, just change it into
R and theta.
our theta, and
Thanks.
that's why you got your square root of pi. And in anything you do in physics, field theory, whatever, it's just a bunch of these types of integrals. Why? Because that's the only thing we know to do. So, since it's Gaussians, it's very easy to calculate the average and the average of the second moment, meaning the variance. Why? Because let's write it this way. guys you can just by putting here u and you can solve it immediately.
With the gamma function, right?
And if you have these types of behavior, what do I do?
Integration
The
by
Feynman.
parts.
Much easier.
You take the derivative with respect to the exponent.
To a.
It's the Feynman trick.
I don't know if it's Feynman's, I think it has been around before him. So once you know this, you know this. And this guy is just by substituting ux squared, du is 2x dx. And then you have a simple integration. If n equals 0, so you have a simple integration on an exponent, the easiest integrals that you have. And if it's a higher, again, derivatives. So you can do the calculation and get the uncertainty relation, and if you do it, you'll get delta x squared times delta k squared equal 1/4, which is the minimal uncertainty that you can get. Where did the h bar disappear?
The
Which
case.
is the k. Okay, so what is left?
Time evolution.
The time evolution. Okay. We have written exactly how it behaves. And here we have dk as you prefer. I just copied my definition of AK, energy, and the Fourier transform. Or if you want the eigenvalues, the only thing that I didn't do here correctly yet is the constants. Move this to here. Okay, so I have an integral to solve.
We're supposed to do also psi of x and t equals 0.
Which is for what did I use psi of x at t?
To find a of k, yes.
Which is here, and this is ak.
Right.
Or
Yes.
we'll just write down here.
Mhm.
That's ak. This guy is That's why you have only one power of h bar. And this is psi k. This is eigenvalue. Okay, so although it might look a bit ugly, it's exactly an integral that we have already performed.
Just have to make change of variable, right?
Right. So I'm writing now only the part that appears in the Gaussian, top part of the Gaussian, and just rearrange didn't do anything. Since I'm lazy, instead of writing this all the time, I'll just call it because I'm doing an integration on K. Everything that appears here for me is a constant, although it changes in time. So to remember that, I'm putting here t, but it's not relevant to the integration.
There is a minus before the with the k square.
The k square, of course. Again, completing it to a square, perform the integration. Okay. Nothing different than we have performed in the previous integration. But here, there is a bit delicate point that I want to pay attention to. Okay, is now the probability of finding the particle Gaussian?
Yes, it's still Gaussian.
Well, you have to be a bit careful. Why?
There's a complex number.
There's a complex number here, and the probability is the absolute value square.
Where
So,
there is a complex. Yeah, exactly.
so it looks innocent, but we have to pay attention that it might be a Gaussian in the end, but it's not immediately trivial that it's a Gaussian, the probability. So let's write down explicitly. So I have a dependence here. To the power of quarter square is just a square root. And let me define why is that? Because it's just the value of delta times its complex conjugate, square root. So I have here the absolute value. F squared and times its complex conjugate. Yeah.
In the first equation, the first row in the denominator, why is it delta squared and not just like
Here?
Yeah.
I think
Like it's less. I think it's reasonable because it's like a standard deviation.
right. It has to be squared.
I guess.
Check it and report next lecture. The best way to see it is from a dimensional analysis. At the end of the day, you'll have your delta x. You have to integrate over psi squared dx in order to get.
Yeah, so the units of size.
So it has.
Because when you complete when you do the SQ, the word that flew through my mind. When you complete the square, you have to minus what you added, and that part has a square.
A square root, right.
So that should be square.
Okay, so I'm left with this term. Let's write it down explicitly. So we started from here, right? Okay, so I'm looking only on this term. And that's fine. It has no imaginary part,
So it goes.
so it's okay. So basically, we do have here a Gaussian that becomes wider and wider. Why it becomes wider? Because of this term.
Shouldn't be each term squared instead of all the terms squared?
Yeah, it should be each term squared. You have here two.
It should be just delta 0 in 4. And 4 divided by 4m in the other.
No, pay attention. This is delta 0 squared. So I wrote it already squared.
Okay.
Okay, so here is just what's written here.
Right, but
After the
Since
procedure,
it is- you're multiplying both terms, right?
I'm multiplying both terms.
So,
So,
any complex number by each
Ju-
multiplied by each complex.
No, you're right. I should write it down to the power of 4.
Right.
Before m.
And that's squared.
And this way. Sorry.
Why?
Because I just multiply this guy by this guy and
Yes, and this covenant. Yes.
no, minus
No, plus.
That's fine. And no, it has to be plus because it has to become
Right.
y. So, although we could have guessed this result from the beginning, it has a bit of detail here that one has to be careful about. Okay, so We know everything that should be known about a free particle. We know what are the eigenvalues and eigenvectors of the Hamiltonian, and we know how it propagates in time. A bit of Gauss. If we would have taken a different wave packet, we might have run into a bit more difficult mathematics, but the principle is the same. What could anyone give me a very simple, intuitive picture why it becomes wider?
Fourier transform. Take it
Because it
Physical,
minimizes its
physical.
energy. Right?
if we know the place exactly, we don't know the momentum.
But why wider? Why doesn't it go?
I think it's okay. So one, there is a dispersion relation, so it's not going to preserve its form because different cases are going to have different velocities. Because the dispersion relation is not linear. Also, due to Ehrenfest's theorem, we know
Simple, much more simple.
To minimize the energy.
No, much more simple. When we built the eigenfunctions of this wave packet, it has plus and minus k's in it. That's that. Everything else is mathematics, but that's a physics. You can't build a wave function with only positive k's.
Right.
Now you can build a wave packet with more weight on positive k's than negative k's, and then the wave function will not only get wider,
But to the right.
but move to the left or to the right, according to how you build it. But the physical reason is simple. You put in as ingredients eigenvalues, eigenvectors that have opposite direction, it must become wider. Okay, so now next step in one-dimensional problem, putting in a potential that's not a simple zero or constant. So I remove 3. So we have V of x. I want to draw something quite general, not the most general potential that one can think about. Goes to some constant at minus infinity, goes to some different constant in plus infinity, and it has a minimum somewhere. Now you can tell me it could have several minimas. Yes. It could go to infinity on the right or to the left. Yes, all of them are possible. But I'm drawing this one because it has all 3 different behaviors that we can see in one-dimensional systems. And we have E and we have X. Let's call it E minus the point where it gets to infinity. Let's call here E plus the point that it goes to infinity on the right hand side. So for E larger than E minus, the spectrum will be continuous. And degenerate. Why continuous? Because it's not limited in space. And same reason why it's degenerate, because there's no difference between going to the right and going to the left. Both are constant. The region where I can reach only one of the limits at infinity, my spectrum is still continuous, but I'm non-degenerate because there is a difference between moving to the right in this case,
Right.
which I can continue forever, and to the left, which I can't. Once I'm in a position where I can't move beyond the potential classically, I'm in a situation where I have discrete energies. One, space is limited. So therefore I'm discrete. And I have no degeneracies because I don't have the symmetry of moving to the right and moving to the left is the same.
Why we can't simulate? Because this is looks symmetrical.
Because it doesn't have the shape of the potential here. I can give you a mathematical answer, which is you have to cause here that the wave function will go to 0 at some point, and that you have to have a combination.
It not have to be symmetrical.
Hmm?
It not
It doesn't have to be symmetrical. That's the easiest. Now, let's look on. So I'm not proving it, but one can prove mathematically these results. It's just the properties of solutions of one-dimensional equations, your differential equations. What will happen in such a potential?
One energy.
Hmm?
Or one energy.
So I'm looking on it and say this is E minus, this is E plus.
We need also the E for the.
It's continuous in this whole range. And it means that basically if I leave a particle here, I can find him after time here. Prepare a wave packet here, it won't stay there. That's tunneling. Yeah.
I don't understand why if the little is E1, if it's low, no, it could stack here. If it's lower than E1, why not?
Because the conditions here are about the behavior in infinity. All modern technology is built on this. Your transistor in the semiconductors is using this property. Diodes, transistors, any solid state electronic device uses this behavior. Okay, yeah.
I didn't quite understand the argument about degeneracy in the left one. Because, okay, I see why it's continuous for the screen. But say in the bottom one, that discrete and then the degenerate.
Mm-hmm.
If I imagine a particle in this region, then it's going to move to the right and then to the left, and it's going to bounce infinitely, right?
We will solve explicitly.
The point is that there is symmetry. It can move to the right and it can move to the left.
And shortly we'll see what this symmetry means. Okay, but it doesn't mean that you have P. Here you get it because here basically you have two solutions that can coexist, something to the left and something to the right. I'm very imprecise because I didn't show you the mathematical behavior, I'm just giving you intuition. Can spread to the two directions. Here basically you will need K plus and K right and K left in order to get somewhere a zero here. To avoid a wave function that continues to infinity. So you have some connection between the two values of K.
Yes, so there's.
You don't have two independent.
But what about the bottom one? It is symmetric.
Okay, as I said, we'll see what symmetric means. And in a moment, we'll define an operator . Okay, so let's look into the bottom part. Okay, here we have states that are confined to the potential. By the way, you have seen the spectrum of hydrogen atom.
Not it.
Hmm?
Just the energies?
Just the energies, right? They are discrete. All of them are discrete, right?
Well, when they're negative.
Exactly. You have there a similar situation. This is a potential, an exaggeration. You have here discrete states. If you remember, it behaves like 1 over n squared. It becomes denser and denser as you get to the 0. And here you have continuous behavior. Why? Because it's above the behaviors of the potential at infinity. Minus 1 over r goes to 0 at infinity. If the energy is above 0, you have continuous states. That's what's called ionizing an hydrogen atom. You kick the electron above some threshold and it becomes basically free. Okay, so what I want to consider now is the case that I have a potential, for simplicity, going to infinity to the left and to the right. So and I want to consider the behavior of the wave function in this case. What do we know? It's discrete and non-degenerate, or at least that's what we claim. So if it's discrete, I have discretized levels, so I can count them with n discrete index. The zero solution doesn't cross the x axis. The first crosses it once, the second crosses it twice, and so on and so forth. It's very useful to check that you didn't do any mistakes. I assume all of you have seen the solution of a particle in a box. That's where the I'm not even given the right
It's square root of 2 over.
square root of 2.
No, I mean, the entire thing is the square root of 2 divided by.
By L, right.
Yeah,
Right.
and
Because look on the sinus. 0, no crossing. Okay, the second solution will have 1 crossing, and so on and so forth. That's not a proof, that's just an illustration. Now I'll say something that I will prove. This, for you, again, one can go and do the mathematical proof. I don't want to go into it here. What I do want to do the proof, because it involves an interesting physical operator, something that you might not have thought about it as an operator, but nevertheless becomes very important in particle physics. And this is the parity operator. So, if the potential has parity, what does it mean? The potential of x and minus x is the same. Then the wave function has a well-defined parity. Now I have to explain what is parity and how I define it. So let's define well, to confuse us with pi, it's defined usually as pi with a hat on it. And it does a very simple operator. You operate the parity operator on a wave function psi, becomes psi of minus x. Is it measurable?
No, I think, because if you measure in the x, you can't measure in the minus x also.
So that's intuition, and that's why intuition kills us.
If it's a medium.
Exactly. I should ask here I should ask the mathematical question. Is it a Hermitian operator? If it's a Hermitian, I would be able to measure it. If it's not, so it's not measurable. Okay. How do I show that it's Hermitian?
Take the conjugate to both sides.
I wrote down the eigenvalue equation.
And it's plus minus 1.
What do that I'll show in a moment, but for now, how do I show from this that it's Hermitian?
If all of them are real, then
If lambda has to be real.
Right.
We did it some previous lecture. It works both ways. I think I said it. If I didn't, so I'm adding it now. So I have to show that lambda is real. what happens if
You obtain the same result.
Get the psi.
but by this equation,
Right.
lambda square psi x.
Which means lambda is plus minus 1.
Pay attention, it's squared. It's not lambda times lambda complex. Therefore, it can't be a phase. Except if the phases are 0 and pi. So these solutions I call solutions with even parity.
Why we call it like this? This is the name. There is a reason.
There's a reason, because even Zugibi do it.
Yes. Because if I take the lambda 1, act like an even function, and lambda minus 1 is like odd function.
What does it tell me here? That
The
psi of minus x is either the same as psi of x,
That's it.
that's even, and minus psi of
Psi of
x, so it's odd. So what else do you want to call it?
Just make sure. Thank you.
Richard, the previous theorem, are there any limitations on the potential of the oscillation theorem? It doesn't have to be even or anything like that. Just that the state is bound.
That it's bound discretely. Okay. Okay, you'll have here a set of eigenfunctions that are even and a set of eigenfunctions that are odd. Now I'll prove you that an integral over sine times cosine is 0. Just because there are two eigenfunctions belonging to different, there are two basis functions that are belonging to different eigenvectors, and they must be 0. The most complicated way to prove this statement. An even function times an odd function has to be, the integral has to be 0.
Over a period, right?
Over my,
But it's have to be streamed. Because yes.
otherwise they are not a basis. Okay, now to your question. Actually, I should have told you, wait a minute. What is the commutation relation between psi and h? H has px squared. That works lovely. Of course it commutes, because it's even operator. It doesn't matter if you change psi of x with psi minus x because it's squared. And if Vx is equal to V minus x, in your case, symmetric potential, then it commutes. What does it mean? That the solution of the Hamiltonian has a defined parity.
And it's also unitary, right?
Psi? Yeah.
The parity operator.
Yeah.
Of course. Of course.
So just completing the trivial particle in a box. Yeah.
Is this C2 algebra?
Yeah. If it sounds unfamiliar to someone, don't worry at this point. Well, here I'm just repeating results that you've heard, and actually I showed it previously. Why do I take here 0 and L? Just because it's easier for sinus. I could put it in the middle, it will become a bit more messy. It's already 25. Let's take 15 and finish it, and after that we'll go to the serious stuff that you haven't seen, harmonic oscillator, the only potential you should know in physics. Of course. Okay, so just before I left, I said I'll quickly run through the solutions of a particle in a box, just because it's a good mental picture to keep about solutions of particles in confining potentials. So, square root of 2 over L is just because of the normalization. K here I'm one-dimensional, so I don't need mx, and n is equal okay, why is that? Just for 0 at the boundaries. Why it must be 0?
Actually, I don't think anything equals 0, because if it equals 0, then the entire function is 0.
At the points, well, no, that's another point that in a moment I'll talk about. Okay, why is it 0 at the boundaries?
Because the potential is infinite, and the particle cannot have infinite energy.
Exactly. So anytime I have infinite energy,
Cannot be there.
it must be 0, the wave function 0. In this particular case, sinus of 0 is 0. It's not a solution, so here I have only 1, 2, and so forth. Okay, what's the energy? Don't believe me? Perform h bar squared times derivative of x squared divided by 2m and see for yourself. Actually, this is an interesting solution. If you want, it's exactly the opposite than the solution for the hydrogen atom. Because here, the n square is on the top, which means that higher in energy, the higher is the separation in level, in possible energies that you see.
Right.
Is there some deep connection?
Yes, there is a solution. There is a reason for it. I don't want to go into the details, but in the next potential that we'll study, which is the harmonic potential, it's exactly between them, meaning that you have a constant level separation there. So if it's too steep, it becomes the higher in energy you go, the larger is the separation. If it's remember if it's concave or concave.
If concave and matter is concave.
It's concave, I think.
It's concave, then it becomes steep. It becomes closer and closer to each other. If it's an harmonic oscillator, it's the exact ratio to give you constant separation.
It has to do the dependency of the potential to some power of the position. It has to.
Of course.
And I think there is the case pi n without the 2, because the upper bound seems equal to 0.
Oh, that's fine.
Yeah.
Why did I write it down? You're completely right. 2 pi you have to have for the e to the to ik. Yeah. Correct. Please correct it. Okay. Before we go into the harmonic oscillator, I just want to give you a very, very hand-waving description of the behavior of a wave function in your favorite potential. To begin with, let's assume that we have a potential that's not infinite, but growing. Okay, in this case, it will get to infinite at infinity, degenerate states. What happens on the boundary? we have a wave function with a value there that's not necessarily 0. The only thing I really know is that if I look deep into the part of the potential which has higher energies than the energy of the wave function, the wave function dies out exponentially. So it will have some behavior, let's say psi of n, without knowing much about it. Let's say n is equal to, let's put here 0. So what do I know? Will be something like that. Why? It has to die out exponentially.
And has to cross 2 times.
It has to cross 2 times the
axis.
0, the x-axis.
And it has to be continuous.
It has to be continuous. So it will be something of this.
And smooth also, because it could be P.
Right. So if I look on it, what I know, the probability of finding this particle anywhere within the potential is not smooth. There are regions where I have higher and lower probability of finding this particle. I even can give a stronger statement. In the case that it's the second eigenvalue, I know that there will be 2 positions where I wouldn't find this particle, because that's the meaning of crossing.
Right, the axis.
Okay. Now let's look on this potential. What do I know? It's continuous. What will be the behavior at infinity here? Dies out exponentially, goes to 0. Right?
How do we assume that it's dying out exponentially?
Because if it's very high compared to my energy, an exponential is the solutions that can come into the game.
But there's the rate of decay should depend on the difference between the energies, right?
Right.
So if the potential keeps increasing, then it's even faster than the exponential.
It could be faster, but I'm talking in generalities. I'm not trying to. I'm trying to, if you get a problem that has these ingredients, so you would be able to see more or less, does your solution make sense or not? Okay, so it will die out here. You want to argue it's stronger than exponentially. At the region where it's flat, it's exponential. That's an exact statement. It continues to grow, it could be even more. And we'll see it actually for the harmonic oscillator, where the potential grows everywhere. In that case, it will die out like a Gaussian. Okay. Coming here. So probably I'll have a stronger probability to be in this pocket because the energy is lower. So I might have such a behavior of the wave function there, depending on how high I am in energy. Here again, I'll have a lower probability to be because it's below. And once I go to infinity, it's like a free particle.
Right.
So very far from it, I can forget about all this intricate behavior. It will define some constant in the phase, but nothing more than that. So I go, I have a particular form of the potential. I have to work hard in order to get the exact wave function, but the general behavior is what I described here. Now, a second type of problems, and that will be discussed in detail in the exercise section, is what happens for a wave function coming from the left, let's say, and hitting this potential. People in optics will immediately see that it's a Fabry-Perot. People not in optics don't understand what I'm talking about. But if you want to see a Fabry-Perot in real life, go to any garage where you have water and a thin film of oils that leaked from a car, and you see a lot of colors. That's exactly this type of effect. In this case, it goes through. Certain colors are reflected in more probability than others, so you see these colors that depends on the angle, so you'll see it differently from any direction. So it comes in part, if I'm looking very far off from this potential, and that's a scattering problem, I know that I'll come out either as a wave traveling to the right, which is called transmitted, or a wave going back to the left, which is called reflected. Usually what is interesting in physics, how much is transmitted, how much is reflected, sometimes the phase that it's reflected and transmitted. But that's a type of question that we're asking, and it's not surprising that it's a complicated behavior which depends on the energy, how much is reflected and how much is transmitted. Depending on the energy, depending on K, meaning depending on color in optics. That's the reason you see these different colors. What is surprising about, and you'll see examples in the exercise, let's say I'm coming here. Classically, the answer will be, doesn't care about what's happening here, will go through. You have only transmission. In quantum mechanics, you'll still get part reflected and part transmitted. Because this guy has an influence on the behavior of the wave function here, and in order to sew up all your solutions here, you'll end up also with a reflected part. And you'll see it in the exercise.
Question?
Sure.
If you have time for something like this, this is weird, right? And what way is there to I know that if you think of it in terms of waves, then it makes sense. But if you think of it in terms of particles, then it seems impossible. What way is there to interpret it such that it's reasonable?
Because, well, I'll go back to the beginning of the course. The description of the world is not of particles, it's of wave functions. So the time dependence of the wave function determines what is the probability of being reflected and transmitted, and a wave depends non-locally on the behavior, and the fact that you have here a potential that's higher from here, although you have more energy, will affect you. Why did you ask it here and not about his problem about tunneling? The same type of question. It's the mirror image. Here you have a potential that you shouldn't be affected by and you're affected. And there you have a potential you shouldn't penetrate through, but because you're a wave, you penetrate through. And wave penetrate. Did you do electromagnetism?
Did waves.
Well, you always have an exponential dying solution, even if you're reflected, right, going into the material. Skin layer, all these. Okay. So these were very general hand-waving descriptions. Now we'll go and solve a problem till then, full mathematics, the harmonic oscillator. And we're doing it, one, because it's nice mathematics. Two, it's almost in any physical problem this creeps up. Third, it's a wonderful opportunity to introduce a description of quantum mechanics that we still haven't yet encountered, and that's creation and annihilation operators, which gives us a step closer to a particle understanding of the behavior.
Can I ask another question?
Sure.
When we get the wave that is higher than the barrier, why there is a thing that's coming back?
Let me give you a simple intuition. Well, the value of K will depend on the energy minus the potential, right? Okay, you have two regions where you have a solution. Let's take the point where you have a discontinuity, okay? You have a different value of K for the solution in this part than in this part, right? Now you want to tie them together, right? Because at this point it has to be continuous. The only way to tie it together is to add a reflected wave here. You've seen it in optics, you've seen it in waves. Same reason.
Thank you.
So we have the harmonic potential. Now, in principle, this is just a constant. I parameterize in this way to connect us with things that we know from classical mechanics. The most important thing, it behaves like x squared times a constant. So, in general, something like that. We will first solve the differential equation. After that, we'll do something new that I find very nice. The creation and annihilation operators. Okay, now you can come and say, well, this is one particular potential out of an infinite number of possible potentials you have in nature. Why do you bother so much about it? The answer is because it creeps up everywhere in physics, and now you'll ask, why does it creep up everywhere in physics?
Because it's the approximation of anything abundant in.
Exactly. And we're usually trying to describe a behavior at low energies. Why? Because we happen to live at low energies. So it comes up again and again and again. Just writing it mathematically, for any potential you have some value of the potential at the minimum, and if you expand it, why don't I have a linear term?
Is it the minimum?
That's it. So that's why harmonic potentials creep in so many different problems in physics. Well, so
And there is also something interesting. It has the same structure in momentum and in space, right? Because the kinetic term will be depending on
both,
this, and the potential will be and since they are conjugated, the differential equation is basically the same up to a constant.
correct, or you call it a bilinear form. A general question in physics not connected to quantum mechanics, but still it creeps out also there. Thermodynamics. Why do we have equal partition
Theorem, right?
theorem? The same reason. Because, okay, let's leave it. So, brute force, not knowing nothing. I have a differential equation. I know to solve differential equations, or at some point I learned and forgot how to solve differential equations. But that's all we have here, right? The Hamiltonian is Now just to understand what we expect here. Okay, it has to be a discrete solution. Why? Because E plus and E minus go to infinity. It has to be discrete. And it has to obey parity. Why? Because this is a potential that has parity. So that's what we expect from the solution. So you know what? I don't want to do now the brute force mathematics. Oh, do it in the end. Because there is something much more interesting to do here. So I'll go back and look in this equation. I have here operators. I'll do something that it's the first time you see it. I'll define two other operators and write down the Hamiltonian in the terms of these two operators. I'm allowed. Are these measurable operators?
No.
No, they're not Hermitian. Looks a bit strange, but at the moment we didn't say that they have any physical meaning. Okay, so why did I define them? And this has a name which we still don't understand. This is the annihilation and creation operators. Why do I write it as A and A dagger?
Because once the conjugate
Of the other, X and P are Hermitian. Therefore, all changes here is a plus to minus. This, I claim, is Hermitian. So I can go and put in the definitions and prove it, but I don't need to.
$8
So this is definitely a Hermitian operator. In a moment I'll show that you can write the Hamiltonian very easily with this operator. So here I'll take the explicit definitions. So I want to write a number operator. Still, I didn't explain why I call it that name, as I didn't explain what is annihilation and creation operators. At the moment I'm doing mathematics. Yeah. Square. Okay. And now the cross term xp and px, is it equal to 0? I've started screening them. These are operators. They're not commutative. You cannot just write 0, 0. Not only you cannot, you shouldn't. So in this case, you have plus, minus, whatever you feel like, plus check me on the sign. Px is a minus, so this is a minus. That's okay. But this guy we have calculated.
IH bar.
Minus the IH.
P operator. I forgot to write
Excuse me?
the P operator, but you forgot to.
P. Right. Correct.
Why it's minus half?
Minus I times I is 1. Minus is minus. M omega deleted. H
yes.
bar is deleted. So
This is the. Let's see this.
pull out H bar omega and see. So that's okay. And this is equal n. So just multiply by h bar omega and move the half to the second side.
Weiss and Dagger, they
No,
same.
sorry,
Same.
Same.
It's H.
And what does it remind us?
The discrete energy spectrum.
It reminds, if we forget about the operator and write it down as a scalar, h bar omega n for photons is just the number of photons, the energy of the wave. We'll see it explicitly.
It's obvious that the Hamiltonian needs to commute with n, right? They share eigenvectors, they...
Well, in a moment, well, the next lecture we'll use it. So at the moment, all we did is basically just a mathematical exercise. We rewrote the Hamiltonian that was written in operators P and X as a couple of different operators A bigger and A. That's all we did. At the moment, we're not even closer to the solution. Well, we are one stage closer. Because commutes obviously with n. Well, I just write down h in terms of n, and n commutes with itself, or n with any scalar here. And if I can solve this eigenvalue and eigenvector equation, then I know the solution for the Hamiltonian, because it will have the same eigenvectors and
And is the eigenvector of the Hamiltonian?
no.
No, the n operator.
The n here is the eigenvector of the n operator. I didn't say anything how it looks. Actually, it has a very ugly structure, therefore I didn't start from the solution of the differential equation. But once I know it, and next lecture we'll see that I don't need actually to write it explicit form, then I would be able, if I can say something about the eigenvalues without writing the explicit forms, I can know the energy spectrum.
This creation and annihilation operators generates a recursion relation, right? With the derivative, because they are derivatives.
I don't want to do derivatives. Derivatives with operators is doable but complicated. I don't want to do that. We'll see what I'm using here in order to solve this equation. And this will repeat itself in field theory, in angular momentum, in many other problems in physics, the same type of logic. Any problem in field theory that has particles in it could be written as a Hamiltonian that has something of this structure, has n, has a number operator in it, although I didn't explain why I call it a number. Okay, so we'll stop here and continue in the next lecture.
Thank you.
Zaznaczyli essence motivation. Najlepiej